As we go through the specification, you'll know the different points that we'll be studying. We're going to start off with 1.1.1, atoms, elements and compounds. So what you need to know is atoms are the simplest part of an element that can exist. They're made up of 3 subatomic particles, protons, neutrons and electrons. Elements are made up of only one type of atom, and they're arranged in the periodic table, and each one has its own symbol. Now when you combine elements together, different elements together, compounds are formed. So when elements form by chemical reactions where elements join together. Common example is sodium reacting with chlorine to make sodium chloride. This is a really bright reaction. It gives out loads of energy because sodium is a very reactive group 1 metal that wants to lose an electron, and group 7 chlorine is a very reactive non-metal that wants to gain an electron. So you take a reactive metal and a non-reactive gas in chlorine, and you react them together, you make an ionic compound called sodium chloride. You'll know it as chip salt or table salt, sodium chloride, NaCl. It's really not important that you know the names of the symbols of the elements because you get a periodic table, but for confidence, and we're all about confidence, it's good for you to know them. So the first 20 elements go like this: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium and calcium. Now you don't have to be able to recite them like that. There's lots of songs available out there for you to learn, but I like to learn the periodic table as if it's a language. So imagine you're going up to someone for the first time and you're going to speak chemistry to them. The first thing you say to them is H-E-L-I-B-E-B, H-E-H-E-L-I-B-E-B. That's a greeting that means the first 5 elements in the periodic table. H-E-L-I-B-E-B. Now if they greet you in a positive way, they will say Knopfnina, carbon, nitrogen, oxygen, fluorine, neon, sodium. Knopfnina, the next one. So if you remember H-E-L-I-B-E-B, Knopfnina, you've learnt the first 11 elements in the periodic table. The next greeting goes like this: Megalsips, magnesium, aluminium, silicon, phosphorus and sulfur. Megalsips, M-G-S-I-S-P-S, sips. And the final greeting would be Clark-K. Cl for chlorine, Ar for argon, K for potassium and Ca for calcium. So put them all together: H-E-L-I-B-E-B, Knopfnina, Megalsips, Clark-K. What I'd like to do is stop there and have a little go at learning the first 20 elements in the periodic table. Next we're looking at specification point 1.1.2, separating mixtures. Now mixtures consist of 2 or more different substances that are not chemically combined. So we need to know about the different separation techniques, and the first one is filtration. Filtration is used to separate a mixture of an insoluble solid and a solution. If you're anything like my class, we did about separating rock salt, and rock salt's made up of sand, the rock, which is insoluble, and salt, which is soluble. So what we did was, first of all, we stirred the rock salt with hot water so as much of the salt would dissolve. Then we filtered it. The filtering removed the insoluble sand from the rock salt. We went on then to separate the salt from the salt solution. So after we filtered it and filtered it again to make sure it was clean, we put it in an evaporating basin and we heated it up. And solids that are soluble in a liquid can be extracted from the solution by evaporating off the salt by heating it. Now, if you've got a mixture of different liquids, then what you need to do is you need to use distillation. Distillation is a process where you heat the liquids to a certain temperature. And if you reach the temperature of the boiling point of one of the liquids, it will come off. It will turn to vapour and then it'll condense, probably in something like a Liebig condenser. So I know in our class what we did was we had a mixture of ethanol and water. And as we heated up the ethanol and water mixture to about 78 degrees, the ethanol evaporated, but the water stayed. And we showed that it was ethanol because it was flammable. Then when we heated it up to 100 degrees, we got the fraction, or we got the separation of water. And we showed it was water because it wasn't flammable. So mixtures, when you put a mixture together, they have the same properties as the individual substances they are made up of. So when you combine different substances in a mixture, they have the same properties. If you put iron and sulfur together, iron will still remain magnetic and you can separate it using a magnet. But if you react it together to make a compound like iron sulfide, then they no longer have the same properties. Compounds have different properties. Remember sodium and chlorine combining to make sodium chloride. Well, sodium is a reactive metal, chlorine is a poisonous gas. But when you put them together, sodium chloride is an ionic compound that you can put on your chips. So separation, when we separate a mixture, it's a physical process. That means no chemical bonds are broken or formed when you're doing the separation. It also means that the physical change can be undone easily. So once you've separated it, you can put the ingredients back together. Stop there, and I'd like you to make sure you can understand and explain the following separation techniques: filtration, crystallization, distillation. Thanks very much for listening. Looking at specification 1.1.3, development of the model of the atom. So, before the electron was discovered, elements were thought to be tiny spheres. And when they developed the idea that there's electrons, these negatively charged subatomic particles within the nucleus, that led them to the idea of a plum pudding model. They kept the sphere idea, but inside the sphere they had tiny electron charges, tiny negative charges, embedded within the sphere. You need to know the plum pudding model is a solid sphere with electrons embedded. Now, the result from the alpha particle scattering experiment, the gold leaf experiment by Ernest Rutherford, led to the understanding of there's a concentrated charge in the centre of the atom, and they called this the nucleus. They also realised there was space in between the atoms. Now, Niels Bohr came up with a suggestion that he said that the electrons orbit the nucleus at a certain distance. Now, he had theoretical calculations, but they agreed with the experimental observations. So you've got an idea, a theory, and you've got the observations experimentally, and when they combine and they agree with each other, then that's what adds weight to a scientific discovery. So that's what Niels Bohr came up with, and it was the atomic model or the nuclear model. The idea there's a nucleus, a concentrated charge in the centre of an atom, and you've got electrons at certain distances from the nucleus. Now, experiments then went on to lead to look at the nucleus in more detail, and it noticed there was a certain amount of positive charges within that nucleus for each atom. Each different atom had a different number of positive charges, and they called them the protons. The positive charge in the nucleus was called the proton. It blows my mind, but 20 years after James Chadwick first suggested it, the evidence came to prove him correct, that there were also other charges, other subatomic particles in the nucleus that didn't have a charge, and they were called neutrons. And that was 20 years after the proposal was put forward by James Chadwick in the first place. Okay, we're looking at specification point 1.1.4, relative electrical charge of subatomic particles. There are 3 subatomic particles you need to know about. First of all, there's the proton, which has a relative charge of +1 and is found in the nucleus. There's the neutron, which is found in the nucleus, but it has no relative charge. And there's the electron that lives in the orbitals or the shells around the nucleus. Remember, Niels Bohr came up with the idea that they were at set distances from the nucleus, and electrons have a relative charge of -1. It's not their actual charge. Their actual charge is a really, really small number, like 10 to the -19. But for us, we're going to compare them. So a proton and an electron have a relative charge of +1 and -1 compared to each other and compared to a neutron. Now, in an atom, the number of electrons is equal to the number of protons. So if you've got the equal number of positive and negative subatomic particles, therefore atoms have no overall charge. Remember, this is atoms. Atoms don't have a charge. There's that old joke that says an atom walks into a bar and says, "Can I have a drink?" And the barman says, "Are you an atom?" He says, "Yeah." He says, "No charge." So the atomic number, each different atom has got a different number of protons. So the atomic number is the number of protons in the nucleus of an atom. Now that's important because isotopes that you'll come across, they've got different numbers of neutrons, and ions can gain or lose electrons to form. So the atomic number is the number of protons. That doesn't change unless you change the element. So different atoms have different number of protons. Ions have different numbers of electrons from their atoms. The rule is this: metal atoms lose electrons to form positive ions, and non-metal ions form negative charges because they gain electrons. And isotopes are atoms of the same element with different neutron numbers. So they have the same number of protons, but a different number of neutrons. Before you move on, make sure you understand the relative charge of the proton, electron and neutron. Make sure you know what the atomic number is. Make sure you know what an atom is, an ion is, and an isotope is. Specification point 1.1.5, size and mass of atoms. So we've already looked at the relative charge of protons, neutrons and electrons. Now you're looking at the relative mass. So protons have a relative mass of 1. Neutrons have a relative mass of 1. But we can state that the relative mass of an electron is very small. An approximation is 1 over 2,000 the mass of a proton or a neutron, 1 over 2,000. What we're going to consider now is something that will probably blow your mind. We're going to look at the radius of an atom and the radius of a nucleus of an atom. Now, these are far too small to be able to see, and we've now developed microscopes that can look at them. And these are the numbers you need to remember. The radius of an atom is about 0.1 nanometers. So if you were to write that in standard form, it'd be 1 times 10 to the power minus 10 meters. The radius of the nucleus of an atom is 1/10,000th that of the size of the atom. So the nucleus is a 10,000th the size of the radius of an atom. So that means 9,999 parts of an atom are actually empty space, the distance between the nucleus and the outside of the atom. That blows my mind. If you were to write the radius of the nucleus of an atom in standard form, it'd be 1 times 10 to the power minus 14 meters in size. Now, when we consider the mass of an atom, what we're doing is we're considering the mass of the protons and the neutrons, because the electrons have such a small mass. So the mass number of an atom is the sum of the protons and the neutrons in that atom. Now, I mentioned it before, but we'll mention it again. There are some atoms that have the same number of protons, but a different number of neutrons, and they are isotopes. So isotopes are atoms of the same element with a different number of neutrons, or different neutron number. Before you go on here, make sure you know what the size of a radius of an atom is. Make sure you know the size of the radius of the nucleus of an atom. And make sure you know the ratio between the size of the atom and the size of the nucleus. Make sure you understand that the mass number is made up of protons and neutrons, and the isotopes have the same number of protons but a different number of neutrons. 1.1.6 Relative atomic mass. When you look at the periodic table for GCSE, you'll notice that copper has got a relative atomic mass of 63.5 and chlorine has got a relative atomic mass of 35.5. Now, this doesn't mean they've got half a subatomic particle, they've got half a neutron or something like that in the nucleus. The relative atomic mass is the mass of the atom, the average mass of the atom, taking into account the abundances of the isotopes of that atom that we know about. Let's consider the example rubidium. There are 2 isotopes in this example for rubidium. We have rubidium-85 and rubidium-87. Let's say 72% of it has been calculated that it's rubidium-85, which means that 28% of it is rubidium-87. The way we calculate it is this. We take the relative atomic mass of the first isotope, 85, and times it by the relative abundance, 72. Then we add it to the relative atomic mass of the second isotope, 87, times by the relative abundance of that isotope, 28. And because it's a percentage of over 100, we divide the answer by 100. In this example, we get an average of 85.6. Another example you'll come across is this. The most common isotopes of chlorine are chlorine-35 and chlorine-37. So on average, there's 75% of chlorine-35 and there's 25% of chlorine-37. So the sum or the calculation would be this. It would be 35 times 75 plus 37 times 25 divided by 100. And if you do that on your calculator, you'll get the answer of 35.5, which is the mass you'll see recorded in the periodic table. 1.1.7. You already know that electrons occupy the shells or energy levels around the nucleus. And you know that different energy levels can hold a different number of electrons. So for instance, the first energy level can hold 2. Then the second and the third energy levels can hold a maximum of 8, and the fourth can hold, well, we'll say at GCSE, it can hold up to 18. If you go on and study A level, you'll learn about S, P, D and F orbitals within each energy level. But don't worry about them for now. So if we take an element, let's say sodium. Sodium is the common example that we go to at GCSE. The atom of sodium contains 11 electrons. That means if we're filling up the electron shells, we fill the first shell first. So the first energy level can hold 2 electrons. Then there's 9 electrons left for sodium, so we put 8 electrons into the second shell, which means we've got 1 electron left to go in the third shell. So the electron configuration for sodium is 281. Which please make sure you can explain the electronic configuration of the first 20 elements. So for instance, aluminium, make sure you know you can work it out, 2.8.3. Carbon, make sure you can work it out, 2.4.